All right, guys, so we're going to pick up right where we left off in the last video and go ahead and attempt example 3. So what's happening here is we have a steel wide flange beam with the dimensions that are given, this cross section right here. And this is the same thing as an I-beam. So if it's subjected to a shear of 80 kilonewtons, plot the shear stress distribution acting over the beam's cross-sectional area. Okay, so in order to plot the shear stress distribution acting over the beam's cross-sectional area, we would have to calculate all these values. So what I did here, this is the answer right here, okay? And this whole part is the answer. But the idea here is, how did we get these values? These are the values that we're trying to solve for, okay? So I'm going to show you how we can get those values. So this really would be part of the solution, but I put it here so we know what we're looking for. Okay, so let's say we didn't have that. What we would know is that, let's see the cross-section. This is the cross-section of the beam. And if we want to see the whole beam, it would look something like this. And then we'd have those top parts for the flanges. Kind of curved. Okay, and then we'd have some cut here, and we have this shear flow, and we know that the shear flow varies parabolically, so we have it gets bigger, bigger, then smaller, smaller, right? So small, bigger, 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 smaller, smaller. Okay, and if we wanted to plot this, it would look something. We said we were going to talk about stress concentration, so what happens here is we have a parabolic function until we get to this crease right here, so this junction between the web and the flange. And then what happens is we kind of shoot up like this, and then we continue with a parabola. So we have some value here, some shear stress value here. If we call this point TB, we'll call this B prime. So we'll say that this, let me actually draw this a little bit better. We're saying that this point right here, right before is B prime, and right after this is point B. And then this maximum point in the middle, right, we know shear is max in the middle, this is point C here. Okay. So this is going to be the B prime, and then this point here where it kind of shoots up, this is going to be tau at B. And then here we have some tau value at C, and since this is symmetric, we don't really need to calculate those two. They're going to be equal to what we get. Okay, so let's take a look at this cross section, at this I shape. And I'm going to actually draw this in 2D here, so we can go ahead and calculate our geometric properties of this. Okay. So let's put in everything we need. We know that this is 0.3. This here is 0.02. And the whole height is, or the inner portion here is 100 to the NA. Another 100. This would be our neutral axis. Alrighty. Okay, so I'll calculate the moment of inertia using parallel axis theorem here. So what we'd have is we'd have 1 over 12 BH cubed. So for the entire thing, we'd have BH cubed, so 0.015 times 0.2 cubed. This is actually going to be just that middle portion there. And then we want to move that to the neutral axis, so we'd have the 1 over 12 times 3 times 0.02 cubed, plus 0.3 times 0.02 times 0.11 squared. And we get a moment of inertia of 155.6 times 10 to the negative 6 meters to the fourth. And this was parallel axis theorem, but feel free to use the hole method, where you cut out the holes as well. So this was parallel axis theorem. Okay, and here, well, actually, I'll write down the other method for you in case you want to see that. If you want to see the other method, all you have to do, so method 2, we would have I equals 1 over 12 0.3 times 0.24, the entire block, that whole rectangle cubed, minus the 2 holes, which would be 1 over 12, then times those inner portions, so 0.3 over 2 minus 0.015 over 2, and then times that width cubed, and that would be 155.6, again, times 10 to the negative 6 meters to the 4th. So you get the same thing. Okay, now we can start with our calculations for stress. So what we want to do, let's start with that B prime. Okay, so for B prime, we know that the width at that section at B prime is 0.3 meters. So let's come back and look at that. Here at B prime, we have this entire width. This is right before, right? This is right before we get to the web area. So here, we're still in this whole top part. So you can see this whole width. That's the entire width of the section. So we're going to use the whole 0.3 meters. And the A prime, that area that we're dealing with, is going to be 0.3 times 0.02 times the thickness of that. Okay, so we can find the Q for B prime. That's the Y bar times A bar, Y bar prime. And this is going to be the distance from that portion here. I can draw it here. The distance from the center of this portion to the neutral axis. That's the Y bar prime, so we're going to get 0.110. And then times that area, which we already calculated as 0.3 times 0.02, and we get 0.660 times 10 to the negative 3 meters cubed. And now we can calculate tau as VQB, this is B prime, over ITB prime equals, and the V, the shear is given as 80, so 80,000, because I'm putting everything into the standard units, times 0.66 times 10 to the negative 3, that was our Q, divided by 155.6 times 10 to the negative 6, times 0.3, and we get an answer in pascals, and to convert it to megapascals, I would divide this by 10 to the 6th, okay, and I would get 1.13 MPa. So this is very important because on your quiz, I'm going to ask you to put everything in certain units, so you need to know this conversion here, okay? And when I tell you to the nearest tenth of a decimal, this is what I want your answer to look like. Okay, so make sure you know all of this really well because the quiz is going to just kind of grade your answers without any partial credit. So I want to make sure you guys kind of take your time on these and you really understand how to do the calculations. Although the quiz is not on topic 6, it's on topics 4 and 5. But you're going to need to know the units. You're going to have to know the units to get the right answer for the quiz. Okay, moving along for B now. So the part now we're past the flange and we're onto the web. So the thickness of the web is that 0.015 meters. We come back here. It's just this thickness right here that's given. And then our Q is actually going to be equal to the QB prime because it's everything above or below that neutral axis, so we don't have to recalculate that. So we can directly get this. We just plug in the 80,000 times the 0.66. I'm sorry, 150. Where did I get this from? 155.6 times 10 to the negative 6 times 0.015. It's an easy calculation if you already did the top one. And again, you would get an answer in pascals, divide by 10 to the 6th, and this gives you megapascals. Okay. Okay, last point is for point C. And here, the thickness at C is also going to be the 0.015, and the QC is going to be the sum of all of those areas times A prime. So here we need to remember that we now have two portions to deal with. Because if this is my NA, this is point C, I now have to deal with this rectangular block and also this rectangular block. So I have two areas I need to deal with. So here my QC is going to be this 0.110 times 0.3 times 0.02 plus 0.05, 0.015 times 0.1, and I'll tell you where I got all these from after I write it down. Okay, so let's go through this. So here, the area 1 we'll say is the red section. So if you see the red section here, the area of the red section is going to be the 15 millimeters times 100. So the 15 millimeters times 100, so this would be the red section. 15 millimeters times 100 times 0.05, so the distance from the center of this to the neutral axis, the whole distance was 100. So it would be 100 divided by 2, which is 50, which is 0.05. The second one, the top portion, would be the 300 multiplied by 20. That's why you see the 0.3 times the 0.02. And then the distance here from this point, the center, to the neutral axis would be 100 plus the distance, the 20 over 2, which is just 110. Okay, and we get that value for that. And now we can plug everything in and we can get tau at point C. That's actually tau max. So if you got a smaller value, you know something was wrong here. And we get 25.2 MPa. And now let's come here and we'll draw that picture that I already showed you. Actually, it's right there. Lesser, a little more, max, lesser, less, least. Okay, and then just note here that most of the shear stress occurs in the web, okay, and it's almost uniform throughout its depth, so it varies from like 22.6 to 25.2. So if we look at, basically, we're not so interested in what's happening here, right? This is what I'm trying to say. Let me write this down. We're not so interested in what's happening here. We're mainly interested in what's happening, what's happening here, which is in the web, in that middle portion. Okay, in this section. Oh, that looks really bad. Hold on. I can just highlight like this. Okay, so we're mostly interested in what's happening there. And you can see that it's not varying by that much, 22.6 to 25.2. So some codes allow us actually to use, instead of calculating these actual stress values, some codes allow us to just use the average shear stress on a cross-section of the web rather than using the shear formula here. Okay, and if you guys remember, we know how to calculate the average shear stress. We learned this really early on as just V over A, okay? So that would be, if we wanted to calculate that, 80 times 10 cubed divided by 0.015, 0.2, and that area is here, 0.015 times 0.2. It's just the, actually I'll show you on here, it's easier. It's just this area. Okay, so it's just the area of the web. And the value you get here is 26.7. So you can see that this is really similar to these values, overestimates by very little bit. Okay, so a lot of codes will just allow you to kind of estimate using this average shear stress as opposed to having to use the shear formula, but in some cases we do need to know what the shear is at a point, so then we do need to use this exact shear formula. Okay, so let's talk about shear flow in built-up members now. Okay, so what a built-up member is, or actually let's talk about shear flow before we talk about built-up members, and then we'll kind of move on to that discussion. So let's consider a simply supported beam here. And let's say that we have some distributed load W that acts along that beam. And let's take a little differential cut here, dx. Okay, so the first thing actually, before we even do that, we can draw our shear and moment. We know our shear and moment is going to look something like this. Okay, we know that this is going to be WL over 2. This here is going to be WL squared over 8. Okay, and let's look at what happens with this cut. Okay, this is a kind of recap again. So we have this little cut, and we have this load W. And what happens when we make the cut, again, we have some internal okay, this would be that dx, and this would be h, the height of that member. Okay, and we know here again, this is a review, we did this last time. Sigma double prime is going to be this m plus dm y over I, let's say. And what we want to do is we want to, so let me draw the stress profile one more time. I know this looks like we already did it, but one more time so I can show you why I'm even talking about this. And basically what's happening here is we want to draw the stress profile on each side, and we see here that if this is the neutral axis, we have this stress in compression over here, we have this in tension down here, okay, this would be our sigma double prime, this would be our sigma prime, and what we want to know now is we want to examine what's happening in between each layer here. So let's say that this was a layered cross-section of all these built-up members. Okay, and what that looks like is this. Let's say this was my cross-section, and I had all of these different layers, and this is my total height h, and this is the thickness t, and let's say these layers are all glued together. Okay, in order for this to act like a beam, remember, for this to behave like a beam, these all need to be glued together. So my question is, so the question here, how much glue is required to keep these, whoa, that's not how you spell these, hold on, these layers together. Okay, that is a question. So we want to examine what's happening in between the layers. Okay, so what we want to do is, once again, I'm trying to see if I should rederive this shear flow formula or just kind of tell you what the equation is. So the idea is, we already derived this last time, so I'm going to come back to what we derived last time. After we apply equilibrium, what happens is we get this function that looks something like this, if you guys remember. Okay, we get something like this. And from this, we continue to derive, and we get this change in force equals dm over I integral of y dA. This is our first moment area, and this is some constant differential change dm. And now, instead of doing dm dx like we did before, what we're going to do, we're still going to have dm dx from one side, but we're going to say that this is df dx, which is equal to dm dx times 1 over I times q. And instead, we're going to leave this in terms of df dx, and this is called little q, which is the shear flow. And this is what is going to tell us how much glue is needed, basically. Okay, so shear flow is we want amount of force per length. This is force per length. That's why we're dividing by dx here. So we get this function or this equation that looks like this, VQ over I, and this is the units for this are Newton per meter or pound per inch, something like this. Okay, and this is a very important equation. Okay, and this is shear flow, so shear flow equation. Okay, so again, this is how much force does it take to keep the cross section together, and this is super, super important for something called built-up shapes. What is a built-up shape? Okay, so let's say for example, I wanted to build an I-beam from 3 steel plates. Okay, I wanted to kind of build these together, something like this. Another steel plate, another steel plate. How much would I need to kind of weld this together? Or what if I wanted to add some C-sections, channel sections, on the tops of this I-beam, and I wanted to connect them, and I would do that on the bottom too. Some channel shape here. I want to know how much weld do I need, one, to hold these together here. What's the weld amount? Okay. And what strength of these bolts? These are bolts here. What are the strength of the bolts that I need? And what we can do to answer this, we can answer this with shear flow. Another thing we can do is, let's say I have a built-up section like this. Okay, oops, not that last one. I have these 4 members, and I want to bolt them as such. Okay, this is, let's say, wood. This is now wood. I would want to know what is the spacing of these nails. So you can see this from a top view. What spacing of nails would I need to make sure that everything stays together? And I can answer all of these questions with shear flow. Okay, some other applications of shear flow, we can find something called the shear center. So I'll show you what that means. Let's say we have this C shape. Okay. Okay, let me see if I can draw this out. Something like that. And then here, let's say this is fixed to a wall. Okay, and this here is basically our shear center is the load applied here only causes bending and no twisting. So it's the point, let's say this is our shear center, and sorry, this is the center of member. Let's say our shear center would be wherever we find it. Let's say this is our shear center. This means that a load applied here only causes bending, no twisting. So the only the direction of the load through this point would be only bending. So some eccentricity from this center, let's say, and this load. Okay, a lot of applications of shear flow, especially for design. So you'll actually see a lot of this in the code, and this is really applicable to like real world examples. So here are some pictures for you. So this first picture this is a wood beam basically with layers. So you can see all of these layers kind of glued together here. You can see all of these layers like this, okay? And this is an oriented strand board for a flange. We call it OSB, oriented strand board. Okay, so these wood fibers are glued together. This is a very cheap way of kind of making this type of beam, okay? This is a black carbon fiber CFRP member here, and this is basically just layers of carbon fiber that have been glued to, or carbon fabric that have been glued together, and this is glued through epoxy, okay? And then we have this aluminum plate here, and this is just 4 L shapes that have been bolted together, and we can't weld aluminum, that's why we see these bolts here. So we need to calculate the spacing between these bolts, and we can do that with shear flow. All right, so let's go ahead and try example 4. Okay, so let's go through this. So you're given, we have a beam, let's say simply supported beam. We have a uniformly distributed load. And we have an allowable shear force of wood screws. Sorry, that says something else. Okay, wood screws for 650 newtons, okay? And what we want to find, we want the minimum required spacing of the screws. So let me show you, I'm going to try my very best to draw this in some 3D way. Okay, so let's see if this works. All right. Okay, and then this would also be back there, kind of. Okay, so what's happening here, basically, is we are screwing this top portion here. These are separate. This is a built-up member. So we're going to screw the top and bottom portions with these nails at some spacing S, okay? And we have some distributed load, pretend I can draw this, some distributed load of 2 kilonewton per meter acting on this. And each one of these bolts is going to be basically going to have to carry, like, let's look at this middle one right here. It's going to have to carry half of the spacing from one side, half of the spacing from the other side, and we call this S. So we're looking for this S basically. And let me give you some values here for this cross section. Actually, let me just redraw this here. So here the top is 100 millimeters. Then we have 30, 150, 30, and the middle is 25. Okay, so we need to convert these internal loads to stress in order to design. And the screws, just so we can see where these screws go, let me actually make sure we know these are built up. The screws are going to go right here and right here throughout that section. Okay, so the first thing we want to do, let's draw our shear and moment diagram. Okay, so again, this is simply supported beam, constant distributed load, simple shear diagram. Actually, we don't even need the moment diagram. I'm not sure why I drew that, but basically the load here, it's 2 kilonewton per meter. The length is 3 meters. That's given in the problem. So here, this would be 3 kilonewton, negative 3 kilonewton. Okay. Okay. And we need to find that S value for one nail. So this one screw would be responsible for half before and half after. So it's going to be responsible for half of whatever's before it and half of whatever's after it. So this is everything before, everything after. It would take half of this total section and half of this total section, right? Okay. So we need to find the force applied on each screw. So what we want to do is the F applied is equal to the shear flow times that spacing X. This is kind of like that length of responsibility of each screw, divided by the number of shear planes. And we'll talk about this in a second. And this has to be less than or equal to the F allowable. And the number of shear planes here, this depends on Q. So I'll show you how to do this. Okay, but this is an important formula. That's what we're going to use. Okay. So first, let's find this F applied. The F applied, VQ over I times S divided by number shear planes less than or equal to what was given in the problem, 650 newtons. The first thing is, let's find what we know we can find, which is I and Q. So the I value here is going to be, you should be really quick at doing these now. So make sure you can reproduce these values. Okay. And then we need to find Q because we want to calculate tau where the connectors are. So I'm going to draw this again before we calculate Q here, so we make sure we know what location that T is going to be. Okay, so the connector is going to be here, right? So we need to calculate basically our value, our Q value from here. So this would be neutral axis, that Y bar. Okay, and this is going to be our option 1. Let's call this our option 1, and I'll show you why later. So if we wanted to calculate Q, this is going to be the sum of all our A prime, Y prime. We've done this before a lot now. So our A prime, 100 times 30. Our Y bar prime is at 105 millimeters minus 15 millimeters equals 90 millimeters. And so our Q okay, and this first moment area is associated with one shear plane, which is at the top. We only found this at the top. So basically the shear plane here means it's only connected, this moment area is only connected to this one shear plane here. This is one shear plane. That's what this value is associated with. Okay. We have another option Okay, the second option, let me actually put this like this. Okay, option 2 is we're going to do this basically sorry, that was like the ugliest way of drawing this, but okay, you get what I'm doing. We're going to choose this as A prime. Okay, so this is option 2. So here, this is 2 shear planes, because you can see I'm connecting 1 and 2, and you guys should be quick at calculating these values now. So you would get here, this would be 25 times 150 times 0, because the centroid of this is 0 away. So we know right away we can't have a shear flow of 0, so option 2 is out. Okay, now we have one more option, which would be to use all of this and all of this, okay? And we would have Q equals A prime, Y prime, and we would get 100 times 30 times 90 times 2, and we would get 540, and this would be for 2 shear planes, and this might work too. So this is going to be option 3, and we're going to try both of these. Okay, so now let's try option 1. We have VQ over I times S divided by number of shear planes. 3 times 0.27 times 10 to the 6 divided by 56.081 times 10 to the 6 times S divided by 1 less than or equal to 650, and we get S required has to be less than or equal to 45 millimeters. This is option 1. Option 2, we get VQ over I times S over number of shear planes. 3, 0.54. You might already see what we're going to get. And we get our S required is less than or equal to 45 millimeters. The same thing. So it doesn't matter what you want to do, you get the same answer both ways. So you pick whatever makes you happy, but both work. Okay, so that actually ends our discussion for transverse shear, and that's the second part of this video and the final part. Okay, let me know if you have any questions, and we will start with the next topic in the next video.